response of a high pass RC network for an exponential input, and the question is, where do we get that exponential input first of all? So we need to have the mathematical expression for that. Where do we get that exponential waveform? For considering a low pass circuit, low pass in the sense input is given to the resistor and output is collected across the capacitor. And if the input is a step input, if we have a step input for this one, the capacitor charges very slowly, and we can find that the voltage across the capacitor will be, for the input, for a step input, the capacitor charges very slowly, and that is exponential in nature. This is the final output voltage appearing across the capacitor, which is a exponential in nature. And when the input voltage is V, as t tends to infinity, the voltage across capacitor reaches the final value. At t equal to 0, without any charging, at t equal to 0, the voltage across capacitor is 0, and as t tends to infinity, the voltage across capacitor reaches the final value. And guys, remember, as we deal with linear wave shaping, we have that capacitor associated with many circuits, and one have to remember that expression for voltage across capacitor at any instance of time. It's like given as Vc equals V final minus of V final minus V initial into e raised to minus t by RC. Guys, we didn't go to this, alright? Please make a note, we still didn't start with this one. Just talking about where to get that exponential waveform and what is the mathematical expression for that exponential waveform. We are talking about that one. Alright, so V final is this one, the final voltage at which the capacitor settles as t tends to infinity, and the input is V volts, so V final will be V minus of, once again, V final will be V minus V initial. This is V not input, this is V initial, and t equal to 0, when the initial voltage across the capacitor will be 0, that is 0 into e raised to minus t. Guys, to avoid confusion, generally RC is a time constant. To avoid confusion, when we start with this one, we come across RC over here, and we have another RC over here, which will be the time constant of the exponential signal. And so there is a small change in the notation over here. This tau RC is denoted with the tau, and RC, the second time when we come across this one, that will be RC, to avoid confusion. Fine. And so finally, what do we have? It's a 0 over here, so this becomes insignificant, and this one, so V from here, so 1 over here minus e raised to minus t upon tau is the expression for voltage across capacitor at any instance of time, which is expression for exponential waveform. So we will make use of this one. The input to the high pass RC network will be Vc, or else this itself will be the input for the high pass RC network, which is given as V times 1 minus e raised to minus t upon tau. So remember, this tau is the time constant of the exponential waveform. Fine. So this is where we get that exponential waveform from, and now this will be acting as input to the high pass RC, which we will be talking about. Fine. And here a small interchange of capacitor and resistor gives us a high pass RC, in the sense input is given to the capacitor and output is collected across the resistor. We have that. Guys, straight away going into the considering the Laplace circuit in S domain. We have Vi of t, V naught of t, not that one. Considering the Laplace circuit, it's a Vi, it's capital V, Vi of S over here, and we got to have that V naught of S at this point, and it's a Xc, should be Xc, which is equal to 1 by j omega C, the reactance of the capacitor, which is still rounded to j omega. It's a S and C. We're gonna consider this reactance. The impedance will be R plus this one in series, right? So we're gonna have that resistor R over here, and a current of I of S will be flowing in the closed loop circuit. Fine. And what do we do with this? So what are we in search of? We are in search of the expression for output voltage expression, the response of this one when the input is exponential input, and that is the input which we have to consider. And for this reason, what to do? Where do we start with? It's once again we have to write an expression considering the potential divider rule, and over the potential divider rule again. Supposing we have two resistors R1 and R2 over here, with the ground over here, with the plus VCC over here. So now the question is, what is the voltage across at this point? V2. How to write that expression for that particular resistor? R2 into the supply voltage VCC upon total resistance R1 plus R2. Same way, same. These two are in straight, a little bent over here. That's the only difference. So writing the same expression for this, the same. R2 is R, R1 is C, Vi of S is R VCC, and V0 of S is R V2. The similar, that kind. Fine. So writing that expression for V0 of S, what do we have? V0 of S, that gives us this resistor. A similar manner, that resistor R into this is what, and so this is how we go for this one. Vi of S upon total impedance R plus 1 upon S C. Fine. V0 of S, that gives. And if you simplify this one, what do we have? R Vi of S as it is, in the sense this one, and the LCM will be SC over here, 1 plus S RC. This SC goes up, alright, so that SC goes up, this one, this S into C comes up. So this is the expression, and there is a small simplification over here, reducing this equation into more standard form, S plus the pole, mentioning the pole over here, in the sense SRC no change, Vi of S no change. It's Vi of S, don't get confused please, I'm confusing you, I'm sorry. Vi of S upon, so guys, taking RC as common from here and from here also, so RC over here, we are left with S plus 1 upon RC, and this gets cancelled, right? This exists no more, and this is more standard representation of in S domain. We can convert this, like if you want to have the inverse Laplace transform of this one, we have a transform pair, Laplace transform and inverse Laplace transform. So what is this Vi of S? We got to get that it's in time domain, and the Laplace domain gives us Vi of S, and that's it. Some partial fractions evaluating A, B, and then we can have that final response of a high pass RC circuit for exponential input. Fine. And here it's in time domain, Vi of t, it's Vi of t. So what will be Vi of S? Simply the Laplace transform of this one. It's a V, capital Vi of S will be V, it's a constant, yeah, where is that? That step input, it's a constant, and Laplace transform of 1, it's 1 upon S minus, it's a Laplace transform of e power minus at. Laplace transform of e power minus at, and the Laplace transform will be 1 upon S. If you have negative, we go for positive A, right? And what is A here? It's a 1 upon tau is A in this case, in this Laplace transform pair. Fine. And so we can write this expression as 1 upon S plus, what is A? This one, this completely, this 1 upon tau is A in this case, and this is the Laplace transform for the exponential input. Now this is plugged in over here for obtaining the expression, the response of a high pass RC circuit for exponential input. So rewriting this one, what do we have? It's V0 of S gonna be no change in this one, S upon S plus 1 upon RC, no change in this one, is multiplied with our Vi of S, which is that one. V also, this V appears over here, into 1 upon guys, V, I'm sorry, let's simplify over here to avoid confusion over there. S into S plus 1 upon tau, fine, and cross multiplying, we have S plus 1 upon tau minus S, and positive, negative s gets cancelled, so we will be left with only this one. So that can be reproduced over here. What do we have? It's a 1 upon tau in the numerator for vi of s. It's already here. It's a s into s plus 1 upon tau is what we plug in the place of vi of s from that very expression for exponential input. And something gets cancelled over here. In this expression, guys, s is supposed to get cancelled. This one, we don't have this anymore. And this one, finally we have, not the finally, the reduced equation, we have v upon tau by s plus 1 upon rc into s plus 1 upon tau. Fine. Now it's a simple pole which can be, now this expression can be split into partial fractions like a upon s plus 1 upon rc plus b upon s plus 1 upon tau. This is the partial expression, partial fraction for this one. Now finding out a and b will help us to get the final expression. So how to evaluate for a? To evaluating a, getting back to this expression, a can be found out by v upon tau upon s plus 1 upon rc into s plus 1 upon tau is multiplied with the a residue. What is a residue? S plus 1 upon rc and subjecting s is equal to minus 1 upon rc. And with this multiplication, this exists no more, this term and this term exists no more, and we are left with 1 of s which is plugged in with this one. Alright, so in this very place, let me write down, we don't have this anymore, and this s is substituted with this one. So what is that? It's a rewriting this one, 1 upon tau, it's a 1 upon tau minus 1 upon rc, and we don't have this anymore. So what if we multiply numerator and denominator, entire denominator with the tau? So we're gonna have this, we're gonna have v upon tau, isn't it? And what if we multiply into tau over here, and also in the denominator, in the sense multiplying both the terms into tau, this gets cancelled. Fine. And this is for a will be equal to, what do we have? It's a v upon 1 minus, guys, we cannot go on write tau upon rc all the time, so a small notation over here. What if we have rc upon tau with the n, representing the ratio rc upon tau with the n, and if with this representation we have to represent over here, we have the reciprocal over here. rc upon tau is n, so we have 1 upon n, so that is written over here, 1 upon n, which can be still simplified as, which can be how to simplify this one? A will be, furthermore a will be equal to, this is 1, and this one we have n over here, n minus 1, and we're gonna have that v, we cannot neglect that v, so this goes up, so this is the, we gonna have that n over here, so this is the value for, this is for a. In the similar way, finding out that for b, with the same approach, what do we have? We have to consider this once again. For b will be equal to v upon tau upon s plus 1 upon rc into s plus 1 upon tau. Once again, for b, the entire, this fraction is multiplied with the b residue, s plus 1 upon tau over here, and with this one, and subjecting whatever the leftover s is substituted with minus 1 upon tau. That's the procedure. So this gets cancelled, we don't have this gets cancelled, and this is the s left over, and we have that in the place of s we're going to substitute this one. In the sense we're going to have r minus 1 upon tau over here. What did we do in the last time for a? We multiplied with the tau, we multiplied with the tau, we multiplied with the tau, and so this gets cancelled, and this is v upon what it is, guys. Once again it's 1 upon n minus 1, and further simplifying this one, nothing changed with the v, and we're going to have n cross multiplying 1 minus n, this n goes up, v into n upon 1 minus n, we need to get to this form, so taking out negative, v upon n, I mean v into n, negative has come out, so n minus 1 is that value for b. This is for b, and those a value and b value is plugged in over here for that v naught. Rewriting this one, so how can be that written as v naught of s over here? What is a value in the denominator? S plus 1 upon rc, no change in that one. So what is a value? It's a v into n upon n minus 1 plus the denominator is as it is, s plus 1 upon tau is as it is, and b we have this value which is minus v into n upon n minus 1, which is in the denominator of the numerator fraction. And yeah, we are there, we are almost there. So what, something can be taken out as common from both the terms for that final expression for v naught of s. Here v naught of s, what we gonna have is v naught of s, that will be equal to, guys, v into n upon n minus 1 can be taken out as common. So what do we have is 1 upon s plus 1 upon rc minus 1 upon s plus 1 upon tau will be left over, right? And what do we want to have? The response, time response, in the sense obtaining the inverse Laplace transform of this expression. V naught of t will be equal, it's a constant, v into n upon n minus 1, nothing to do with this one, it's a standard Laplace pair. Previously, like e raised to Laplace transform of e raised to minus at, that will be equal to 1 upon s plus a, and inverse Laplace transform in Laplace transform this one. So inverse Laplace transform of this one will be, this gets cancelled, and inverse Laplace transform of 1 upon s plus a will get back to over here. So we have this, and applying the inverse Laplace transform of this one, we got to reach over here, and this is our t. In the sense, how to write down that? E raised to minus t upon r c, and this one negative. Once again this one, this is our a, so this can be written as e raised to minus t upon tau. 1 by tau, 1 upon tau is our a in that case. And another, this can be substituted with something else, and this one can be substituted in something else with something else. Let's see what is that. What if, okay, this rc upon tau is n, that's okay. What if we have t upon tau with another, like what if we have that to be x, t upon tau, what do we have? So what will be x on n? X is t on tau upon rc upon tau, so this gets cancelled, right? Tau gets cancelled, and we will have t upon rc. In the sense, t upon rc we can plug in with this one. So here comes what is that? V times n upon n minus 1, and this entire, this one, I mean with the negative, I mean e raised to negative as it is, t on rc, that will be x on n minus of, guys, this one, e raised to minus of t on tau x. So this is the v naught of t, that response of a high pass RC network for exponential input. That's it.